Hello everyone, I'm Chen Yinghuan from Institute of Software, Chinese Academy of Science. My report name is Hilbert Sampling Algorithms for Dynamic Graph Sampling. When do we need to use the dynamic graph sampling? In temporal graph random walk and involving graph random walk, where temporal graphs are graphs attached with time instance, and the involving graphs are graphs with dynamic edge modification. Firstly, we introduce the definition of temporal graphs. Temporal graphs are graphs attached with time instance in edges. Using flat map as an example, the start time and the arriving time of each flight can be the time instance of each edge. For social network, the message passing time can be the time instance of each edge. The paths in temporal graphs have to satisfy the time constraints, which means the increasing time along the path. Then random walks on temporal graphs is a temporal path starting from a certain edge and then randomly sample new edges along the path. On sampling, the candidate edge set contains efficient edge for each sampling which satisfies the time constraints. In other words, the time instance of candidate edges are larger than the previous arriving time. Then the sampling of random walks will follow the transition probability, which is the probability distribution of edges on each candidate edge sites. We can see that this is also decided by time and the weight is exponential to the time instance. For example, on social network, when arriving at vertex 7 from vertex 9 at time 4, the candidate edge sites is only 4, 5, 6, and the weight distribution is 5, 6, and 7. The sampling on vertex 7 at time 4, we are using the ITS or Alice method or rejection sampling on the transition probability according to the weight distribution. There exist some challenges on current sampling technologies such as the rejection sampling ITS and Alice method. Specifically, for rejection sampling, the transition probability exposure to the time instance, which will lead to a large number of trials to be accepted. The accepted trial number is nearly OD, where D is the degree number of current sampling, which is too large. Then, for ITS, the time complexity is also log D, and also had to be rebuilt for different candidate sets according to different arriving time instance. For the Alice table, we also need to rebuild all versions of Alice tables according to different candidate sites and different arriving time. The space overhead is nearly 1 trillion bytes for Alice table constructions. In conclusion, there exists dynamic sampling challenge and dynamic candidate edge site challenge. The dynamic sampling is caused by dynamic transition probability. The dynamic candidate site challenge is caused by different arriving time. To solve above challenges, this paper proposes the persistent Alice table to handle the dynamic sampling and the dynamic candidate edge site. It partitions the nervers of each vertex into different trunks according to a fixed size. Then we construct the Alice table inside each trunk and create a ITS array between different trunks. For example, the nervers of vertex 7 is partitioned into 4 trunks, and each trunk has the size 2. Then the Alice table is created for each trunk, and its prefix sum array is created for different trunks. On sampling, we firstly use ITS to sample a trunk according to the candidate edge site with O log D divide trunk size time complexity, and then sampling inside each trunk using the Alice table with OE time complexity. For example, when sampling on vertex 7 and the random number is 12, then we will sample the first trunk and use Alice table inside it with OE time complexity. The overall sampling complexity of persistent Alice table is O log D divide trunk size. Then we can further optimize the persistent Alice table to reduce the time complexity. Here we propose a hierarchical persistent list table. We create log d number of persistent list tables with each trunk has a fixed size as nth power of 2. Then we create a list table inside each trunk and create prefix sum array between each trunk. On sampling, we only need to binary decompose the length of the candidate edge site length. Then the length is divided into several chunks with the length of the nth power of 2. Then we should use the ITS to sample in the chunk of interest and then sample the corresponding edge inside the trunk by a list table. The time complexity of our sampling is only O log d, where d is the degree number, which is close to constraint. This is because after binary decomposition, there are only log d chunks, and the ITS on it only needs O log d time complexity. How to rapidly identify the candidate set? We create an auxiliary index for fast list table searching. We only need to preprocess the binary decomposition of integer from 1 to the maximum degree number. This is because the length of the candidate edge set is up to the degree number. With the help of the auxiliary index, we can recognize the candidate list table on constraint time complexity. The space complexity is only up to OD log D, with D is the maximum degree number. For the workflow of T, it firstly prepares data structures including the persistent list table, hierarchical persistent list table, and auxiliary index. On summary, it will firstly access the auxiliary index of vertex S. Then it accesses the hierarchical persistent list table. Thirdly, it performs sampling on the hierarchical persistent list table with O log D time complexity. Finally, it will using the new selected vertex and repeat the above process. Not only this, T can also support the streaming graph data flow by incrementally update the hierarchical persistent list table. On overall performance, T can have up to 3 orders of magnitude speedups than current works, such as Graph Worker, which is published at ATC, and NetKing, which is published at SOSP. T can endure higher speedups on bigger graphs because the time complexity of sampling is optimized from OD to O log D, and the larger graphs usually have larger degree number. Then, how to deal with the dynamic edge modification? We can use the incremental hierarchical persistent list table updating strategy to update the heap-packed data structures when facing edge modification, including edge inserting and edge deletion. For edge inserting, we can create a new heap-packs and merge the new heap-packs into the old heap-packs. Then, for edge deletion, we can directly delete the corresponding heap-packs. In detail, for edge inserting, when adding new edges for vertex 7, such as edges from 7 to 8 and from vertex 7 to 12, then we can create heap-packs consisting edges from 8 to 12. Then we can merge the newly added one into the old one. For example, the trunk of the new one, which contains 8, 9, 10, 11, can be merged with the trunk of the old one, which contains 3, 4, 5, 6, to get a new trunk, which contains the edges from 3 to 11. Then, in that case, each new edge will only be operated with O log time complexity with a very low overhead. Then, for edge deletion, we directly remove the trunk containing the deleted edge. For example, when deleting the edge from vertex 7 to 0, 1, 2, 3, the trunks containing 0, 1, 2, 3 will be directly deleted. This is correct because we arrange the edges by time decreasing and each Edge candidate set can be the binary decomposition. The time complexity for each edge deletion is also log D. Then, how to deal with the inverting graph without time instance? We proposed a radix-based bias factorization strategy which uses binary decomposition for each edge weight, and each weight will be divided into different nth power of 2. Then, for all novel edges of each vertex, one ranging from 0 to log D, each nth power of 2 will get a group of edges, and we can easily to get the sum of them by the prefix sum number. For different nth power of 2, we can create a prefix sum array of them, and which contains only log D number by ITS. On sampling, we only need to firstly use the ITS on the prefix sum array of different groups using O log D time complexity and directly index the sampled edge inside each group. For edge inserting, we also use the binary decomposition by dividing the edge weight into log D parts and insert them into each groups. For edge deletion, we also remove the weight of each group, and we only need to move the last one of each group into the deleted one to avoid rebuilding the group. The process is also OD time complexity. On evaluation, our work, which is named as Bingo, can get up to 105.49 times speedups. That's all. Thank you for your listening.